I'd like to talk today about something which sounds very formal, scale and conformal invariance. But as you will see, sort of these things have concrete applications, which I think are quite interesting and are still sort of current interest. But to introduce the subject, I start with something extremely simple, which you all know, of course, the hydrogen atom. But let's take the hydrogen atom not in 3 dimensions as you know it, but in 4 dimensions. Now, in 4 dimensions, the interaction between 2 point charges is 1 over r cubed. The potential is 1 over r cubed. And so the Hamiltonian you get, is has the usual kinetic term plus a 1 over r cubed term, r squared term, with a constant, which is in a way the generalization of the Bose radius, but which is now dimensionless. Now, if you look at this Hamiltonian, you see immediately that if I scale lengths by a factor b, the whole Hamiltonian scales like 1 over b squared. So this is a scale invariant system, and this implies that the spectrum is continuous. You cannot have a discrete spectrum in this case. So basically, the hydrogen atom in 4 dimensions would not have discrete states. Hydrogen wouldn't be bound. It's not the whole truth. Actually, if this coefficient is less than 2, so the strength here is too large, then actually sort of what happens is that sort of the electron would dump into the proton, and you would have to sort of in a way save this by introducing a finite proton radius. Well, of course, fortunately, in real life, we are not living in 4 dimensions. We are in 3 dimensions, and we don't care about the proton radius, at least to lowest order in the treatment of the spectrum of hydrogen. But I mean, a Hamiltonian of this type is actually sort of not a pure academic exercise. It appears, if you look at the interaction of a charge, a point charge, with a dipole. Of course, then you have a 1 over r squared interaction, and that it is then angle dependent, but the physics is a bit, or is relatively similar to what I discuss here. Namely, what you find is then that this case means that basically binding 1 electron to, say, a polar molecule is only possible if the electric dipole moment of this polar molecule is larger than about 2 dBi. Actually, in '94, there were experiments on this here in Paris Nord, in Villa-Teneuse, in a way showing this, that basically with Rydberg atoms sort of interacting with polar molecules. So this is not a purely academic example. Now, the usual example where sort of we find scale invariance is in thermodynamic statistical physics, where we tune a system right to its critical point at Tc. Correlation length is infinite, and then correlations of an order parameter decay with some power, which is usually written in terms of this d minus 2, which is the power obtained by doing mean field theory, plus what is called an anomalous dimension. And you see, if this holds, then the correlation function at a scaled coordinate just is the original correlation function with a factor b to this strange power divided through. An example, a concrete example, is that in a way is relevant in cold gases is, of course, if you take a 2D superfluid below the BKT transition, then the correlation function here of the order parameter, which is the off-diagonal long-range order I mentioned in the first lecture, decays below this transition temperature with a power law with some exponent eta, which now, however, is itself a function of temperature. So you don't have 1 critical point, but you have a whole series of critical points. The whole line T less than Tc is a series of critical points. One comment here is, of course, anomalous dimensions is something that, I mean, usually sort of one is not used to, and one, of course, we don't measure sort of length in centimeter to the whatever 1/2 or something like that. What it means is, you see it here, I've written it in dimensionless form. This thing has dimensionless density, and so you need some microscopic length to make this sensible. And this is actually a general statement that if you have a system with an anomalous dimension and a 2D superfluid is 1 below Tc, then the microscopic length never drops out. Or a microscopic length never drops out. In this case, it would be some effective healing length where you cross over from sort of collective to linear to quadratic behavior in the single particle spectrum. So this is scale invariance. I just increase length by a factor b, and then things scale down by some factor to some power. Question is, what is conformal invariance? That's usually sort of not in the focus of interest apart from a few specialists. In conformal transformations, what you do is you make a length rescaling, but the length rescaling factor is itself position dependent. And you do it in such a way as to preserve angles. And formally, you can say, I make a change to new coordinates such that the new metric is some b squared, which may be itself spatially dependent, but still remains diagonal. That's sort of a formal definition, so-called Weil transformations. And if correlation functions, in a way, obey a generalized form of this scale invariance, namely that under this transformation, you rescale the correlation function by locally varying factors b of x and b of y with some power delta, then this theory is called conformally invariant. It's pretty abstract, and I mean, many people sort of have spent a long time about sort of, in a way, finding the so-called primary operators and the so-called scaling dimensions. And basically, if you know this for a certain theory, you know the whole theory in statistical physics. But let me, and the example here is sort of, in a way, distinguishing scale invariance, just blow up the system by a factor, whatever, 2, or, I mean, distort it such that angles are preserved. Now, one example that sort of is known, but not in a way widely known, is that electrodynamics in free space, Maxwell's theory, is actually both scale and conformal invariant. It's scale invariant because if you take, for instance, the correlation function of the field strength tensor, this decays like sort of the distance between these points to the 1 over the 4th power. That's effectively the Casimir effect, which is hidden in that. But you know more. It also fixes that scale invariance, but conformal invariance fixes also, in a way, the complete tensor structure of this correlation function. That's something that was discovered by Weil in 1917. And so the general belief often is that, okay, if a system is scale invariant, then it's also conformal invariant. But to check it is non-trivial. There's actually a simple example in physics where this rule does not hold. Namely, the theory of elastic continua in 3 dimensions is scale invariant. Phonons are massless, scale invariance, but it's not conformal invariance. And it would be sort of really nice French physics of the 19th century, the Lamé coefficient, the Cauchy stress tensor, and the Poisson ratio to explain this, but in a way it goes too far. So I'll, in a way, refrain from discussing this. But there are systems where basically this transition from scale, simple systems where the transition from scale to conformal invariance does not hold. And in particular, sort of now for this electrodynamics, what you see, the invariance group that one usually knows for relativistic theories is extended by 5 additional generators. One is the simple scaling, but then conformal invariance gives 4 additional generators. So it's quite an enlargement of the symmetry. Okay, so what I want to do here in this lecture is to say, I mean, is anything like this, I mean, relevant sort of in a many-body context of non-relativistic particles, of course. We are interested in cold gases. I mean, can one generalize such concepts to many-body theory? What is scale and conformal invariance in a non-relativistic many-body context? And scale invariance is kind of clear. I mean, we have seen this in the hydrogen atom, just rescale lengths by a factor b, then the Hamiltonian correspondingly rescales by 1 over b squared. And what I will argue is that, I mean, in this case, for non-relativistic many-body physics, if you have scale invariance, then this automatically implies the reduced conformal invariance. So in a way, there's no new, at least if you have sort of bosons or, I mean, fermions where you can label your spins with some degree of freedom, which sort of in a way does not have anything to do with sort of space-time. And then I will show 2 examples where this scale and conformal invariance in the many-body system shows up, both in equilibrium thermodynamics and in the dynamics. And then, in a way, in the second half of the lecture, I will show that, I mean, these things have also implications for beyond the simple sort of ideal fluids one is often considering in cold gases, namely scale and conformal invariance have implications for transport coefficients, viscosity and heat conductivity. These are the 2 examples I will discuss. So let's start in a way with the formal definition of scale invariance for a many-body system, which just says, okay, I have a Hamiltonian which depends on n coordinates for n particles, and if I rescale lengths by a factor b, the Hamiltonian just is reduced by a factor 1 over b squared. Now, okay, you see, this is of course a quite strong condition, even with interactions. Of course, again, as in any sort of symmetry in quantum mechanics, we can form it in terms of some commutators. Usually, you know, if there is a conserved quantity, the commutator with the Hamiltonian is 0. Here, of course, the Hamiltonian is not invariant, it changes by a factor. So the relevant commutator of the Hamiltonian with the operator which produces an infinitesimal rescaling of coordinates, this dilatation operator, as it is called, is just 2 times a. The 2 just comes from expanding out this b. And the generators of dilatations can be written in a local way as an integral of the momentum density. And you see, if it were not for this x here, this would just be the momentum operator, which generates translations. Now you make a dilatation, so you have an additional x here. So formally, you can say, okay, a Hamiltonian in a many-body system is scale invariant if this relation holds. But in a way, now we have a system not as the hydrogen atom in 4D. We have sort of field theory, if you wish. So there's some x dependence. And so this thing has to be formulated also in a local manner. Just like, okay, you know, particle conservation means the Hamiltonian commutes with the particle number, but then we derive a local continuity equation from that. What's that here? Well, turns out that from this, there is a local continuity equation for some dilatation density and some dilatation current, which are nasty objects, which I will not write down. And you will find that this condition then is obeyed if and only if the microscopic energy density of the many-body system is equal to the trace of the so-called stress tensor. The stress tensor is the tensor which determines sort of, in a way, the momentum balance. I will not write down the microscopic expressions for this stress tensor, which actually were written down first in a many-body system by Martin and Zwerger in a famous paper in '59. I just remark that, okay, this condition is an operator condition. It holds identically for all states, not just in equilibrium or something like that. It holds for all states. And basically it says for a scale invariant system, the trace of this energy, stress tensor must be twice the total energy density locally. It generalizes a relation which is well known in relativistic theories. The trace of the energy momentum tensor is 0. In electrodynamics, perhaps you know that the radiation pressure is 1/3 of the energy density. That's one consequence of this relation. But this relation is much stronger. It tells you this condition holds for all sort of solutions of Maxwell's equation, time-dependent, whatever you have. Okay, let's go. What are the conditions that this relation holds in the many-body system? Well, if you insert the microscopic expression for this stress tensor, you find, not surprisingly, that if you have two-body interactions which are rotation invariant, the two-body potential must be a homogeneous function of degree -2. And apart from the trivial case of non-interacting particles, which we are not interested in, the only two solutions are either you take 1 over r² interactions in any dimension with any strength, or you take a delta function interaction in 2 dimensions, where, of course, this also holds. The fact that delta functions in 2 dimensions give rise to a scale invariant many-body problem was realized by Pitaevsky and Roche in an influential paper in '98. And I will essentially take this example, because this is an example which is of course describes a real system, namely sort of 2D gases with short-range interactions. The case here with the 1 over r² is actually well known also in the literature. It's called the Calagero-Sutherland-Moser model. It's well studied in 1 dimension, where actually then you have sort of, in a way, you can solve it exactly, and there's lots of things you know about it. In higher dimensions, actually sort of the thermodynamics which would follow from that model is ill-defined, because it decays too slowly. And so I will not discuss that further, in particular, since there is no experimental or no realization of such a potential ever there. Now, you can ask, I mean, okay, now this is scale invariance, and can we have a situation like we have in elastic continua? Could scale invariance alone not be sufficient for having further this conformal invariance? The answer is no, and in a way the whole story goes back to a thesis of Niederer in '72, where he discussed the symmetries, the most general symmetries that you can have for the free one-particle Schrödinger equation. So it looks simple, but it's actually quite a complicated beast. And what he showed, what he showed is that those symmetries we all know of, I mean, time translation, spatial translation for free particles, the rescaling, and the Galilei transformation, there are two further symmetries that are there. One is scale invariance, and the other one is what I call an expansion, which is essentially a Galilei transformation in which sort of the Galilei velocity is not just a constant, but is in a way itself spatially dependent. So it's like in Hubble expansion. The velocity field is just a constant times x. That turns out to be a symmetry of the free Schrödinger equation, just a one-particle Schrödinger equation, and you can decompose that symmetry actually in two inversions and an intermediate time translation. But you can only do it sort of, there's only one parameter here. And the generator of this transformation is essentially written now in a many-body formulation, the second moment of the density. And you see now, of course, this is of course smells already interesting, because for cold gases in a trap, I mean, that's precisely sort of the potential which a trap makes, an isotropic trap. And what Niederer showed is that the Galilei group can, for free particles, can always be extended by these two generators, and that in particular D, C, and H together, they form a closed subalgebra of this group, and the symmetry is that of the Lorentz group in 2+1 dimensions, two Lorentz boosts in some plane, and then a rotation in the direction transverse to that. Now, if you want to know, I mean, what's going on at the many-body level, so if you want for a field theory, then, I mean, there was a paper by Hagen in the same year, where he actually showed explicitly, these are all things which, I mean, are quite technical, and I will not go into the data. I'm just telling you the results. For spinless particles, if you are not bosons or fermions with just up and down spins, scale invariance always implies conformal invariance. So there's, I write here, there's no new conservation law. Of course, there is a new law like this. So there's some conformal density and a conformal current. But this conservation law for this is obeyed using other conservation laws, energy conservation, Galilei transformation, all what you have, again, by only this condition. So if you have this condition, you are done. So basically, conformal invariance you always, is always a consequence of scale invariance in this case, which is, of course, not true in general theories. Now, if it were for either Bose or two-component Fermi gases in 2D with delta function interactions, it would already be nice, but things are actually scale invariant many-body systems are actually much wider, and this was realized by, well, Felix Werner and Yvonne Castin, and independently by Son and Wingate 8 years after Roche and Pietrewski. Namely, they said they're so-called unitary gases, and now generalized the notion of unitary gases. I say there is a whole class of unitary gases, either in 1 or in 3 dimensions. Namely, how do we define those? You say, well, the Hamiltonian is that of non-interacting particles. Well, of course, that's scale invariant. But you know, I mean, to specify a system, you have to say more than just giving the Hamiltonian. You have to say, I mean, what are the wave functions? What's the states you're looking at? And the states you're looking at are now sort of restricted in the following way, that you say you have many-body wave function, I take bosons in the simplest case, such that if I take any of these two particles close together, the wave function should vanish with a power 2 minus d, and the next term 4 minus d. In 3 dimensions, that's the usual way. There's a 1 over r, and then the next term is not a constant, but already starts linear in r. That's what I'm saying here. So the scattering length is infinite. You can do the same thing so there's 3 dimensions. In 1 dimension, you can say, well, I enforce the wave function to be vanishing with a cusp at the origin, and the corrections to that are cubic. Then you are sitting sort of in a way at 0, 1D scattering length means infinite strength of the repulsion. And so there's a whole zoo, if you wish, of scale invariant gases that can be realized with short-range interactions in 1D and in 3D. And I've sort of given the list down here. For Bose gases, let's first discuss the one-dimensional case. The realization that has been sort of looked at in detail so far is the Tonks-Girardot gas. You just take bosons with strong repulsion. This system fermionizes. There's a chemical potential which is effectively given by the Fermi energy of the equivalent one-component Fermi system. But there are two other examples. Namely, you can either take an attractive Fermi gas in one dimension, sort of two-component, then they will form bound states. These bound states, if they are dilute, behave like hardcore bosons. And then you get a Tonks-Girardot gas of dimers with a chemical potential which is 1/4 of the Fermi energy of the original Fermi gas. And you can take the opposite limit. You take a two-component Fermi gas in one dimension where you say there's an infinite strength repulsion between up and down spins. Then, I mean, in a way, even the up and down spin combination fermionizes, and in a way you cannot fill, in a way, two Fermi Cs independently. You have to fill sort of the whole thing into one Fermi C. Then the Fermi wave vector doubles, and the corresponding chemical potential is 4 times. These are sort of, in a way, the 3 unitary gases in 1D. What about 3D? Well, we can look at the Bose gas in at infinite scattering length. That's problematic because, as I've also explained in the first lecture, and bosons sort of near infinite scattering length have sort of bound states of whatever sort. You have 3-body, 4-body, and so on. And so in a way, the system isn't stable. So it's stable only in at reasonably sort of non-degenerate limit, and you can discuss certain properties of that. And you get scale invariance properties, but in a way it's not, there's no well-defined ground state. There is one for attractive fermions. This is the famous unitary Fermi gas. Attractive fermions in 3 dimensions, which bind sort of to Cooper pairs in the ground state, and the chemical potential is some universal number times the bare Fermi energy. And what I also emphasize is, in principle, as a theory problem, you can also look at the repulsive branch of this. This is something which is also a scale invariant problem. You go to KFA plus infinity. So you trace out the bound state and you look at, in a way, what is the energy of a repulsive Fermi gas once KFA becomes large compared to 1, eliminating the bound state which is there in reality. Formally, this is a well-defined problem, and it's sort of not a 100% in a way solved problem to this day. There were speculations about that this problem gives rise to ferromagnetism after some experiments done at MIT in Wolfgang Ketter's group in 2009. The general conclusion was that these experiments, or these experiments in the end were hampered by the fact that there was a strong decay to the bound state. If you could sort of eliminate that, then there's still the question, I mean, would that system in a way show a bit like this system here, the repulsive Fermi gas, where you have essentially up-down fermionization? That's not very well known. But it's hard to, I mean, mathematically you can define it and it would be a scale invariant system. Physically, it's hard to sort of test. So in a way, what I'm saying here is, apart from the 2D Bose gas and 2D two-component Fermi gas, there's a whole, slew of other scale invariant many-body systems that one can realize in cold gases. And I will, in a way, now give sort of, for 2 concrete examples, one of the sort of consequences. Namely, I've told you that scale invariance gives this relation, and in particular now, if you take an equilibrium average and say you are in thermal equilibrium, this tells you that twice the energy, the internal energy, is d times c, d is just the dimension of the system, how many elements in this trace appear, times pressure times volume. So that's the, if you wish, the equation of state for an ideal gas, but it holds for a scale invariant system. Now, you can use this to eliminate essentially from this quite general thermodynamic relation and determine sort of temperature for of this system in terms of a very funny form of the equation of state, where you integrate the pressure and you have to know what is the compressibility of the system as a function of pressure. In fact, in a way, this was first used by Martin Zwerger and collaborators together with Felix in 2012. Actually, if you look at the history, there was a textbook by Max Planck in 1897, where he actually showed at that time it was important to know, I mean, how can you determine absolute temperature from a measurement on a system where you don't know the equation of state? How can you fix the absolute temperature? And Planck essentially sort of uses that and shows that by integrating such an equation, you can, if you fix absolute temperature at one point, then by measuring the integration version of state, you can go on and then measure absolute temperature as a function of this parameter. And essentially sort of what is done here is following sort of the recipe which Planck, in a way, suggested in his textbook in 1897. And so what you get is a universal form of an equation of state for such a system, which I've drawn here for the three-dimensional unitary Fermi gas, where pressure is in dimensionless units normalized to the pressure of the non-interacting Fermi gas is here on the horizontal axis, and this compressibility, again normalized to the one of the non-interacting Fermi gas, is here. And these data here are measured from measuring density profiles. If you know the density profile in a trap, you can infer n as a function of the chemical potential. If you integrate that once, you get the pressure. If you differentiate it once, you get the compressibility, and eliminate this mu, you get this universal equation of state. And you see here this equation of state, the points are the data, and the red, respectively the green below TC, is the theory of something that we have developed in 2007. Of course, at that time, we didn't plot it in this way, but you see it agrees perfectly. So without any, and so this is quite remarkable. There's no adjustable parameter here, either in theory or in experiment. It agrees quite well. Of course, you see there is some, the superfluid transition here shows up as a peak, and we cannot resolve sort of the details of this peak, but I mean, it agrees very well, and you can sort of read off what is a so-called Birch parameter 0.37 from this data. A similar experiment has been done a few years later here in the group at Collège de France, Rémy Dupucois, with Jean, for two-dimensional Bose gases, where again, you can plot here this, what is called the x-1, which is the dimensionless pressure, here as a function with here on the vertical axis, the compressibility. And you see the line is just essentially going up. There is no indication for some sort of singularity. This is a 2D system. It definitely has a superfluid transition. So in the regime below here, this is a superfluid, but the superfluid transition in this case does not show up at the equation of state level. But in a way, you can rescale all different densities and temperature and all obey a single universal curve, which is determined here. In this case, there is one parameter here which determines, sort of, if you wish, the endpoint of this curve, which is the effective interaction strength in this 2D system, this G2 tilde, which in this case was small, 0.1. So in a way, the curve, here you see the curve doesn't go below this. You cannot go below the ground state pressure. Here, the ground state pressure is almost invisible. Finite ground state pressure is almost invisible. At the dynamical level, and this is something that was already discussed by Pitayevsky and Roche, a scale invariant many-body system has these the two generators for conformal and for dilatation symmetries, and the Hamiltonian, they form an algebra. And as mentioned, the Hamiltonian in an isotropic trap has the form, the standard scale invariant Hamiltonian, plus this term from this C, which is just the second moment of the density multiplied with the frequency squared of the isotropic trap. If you build operators, essentially this Hamiltonian in units of 2 h bar omega, a L1, which is L3 minus essentially the C, and then L2, which is essentially the dilatation operator, this is an algebra which is similar to the rotation algebra, but there's a minus sign, important minus sign. So it's not SU2, but it's sort of SU11. But it's easy sort of to derive the solve the Heisenberg equation of motion for these operators, and you find that this C, which from this relation is just the difference L3 minus L1, and L3 is conserved because this is the Hamiltonian. The L1 just oscillates at the frequency 2 omega. And this has been tested quite nicely sort of 2 years ago in the group here, where you can prepare a two-dimensional gas in some arbitrary shape, maybe a square here, then let it evolve. It evolves into something that is sort of not so clear in a harmonic trap, isotropic harmonic trap. And if you measure from the density profile, just integrating this, the interaction, the potential energy, so the energy in the trap, this oscillates quite nicely with a period 2 omega. So it's a beautiful demonstration of scale invariance for the system. One of the surprising observations of this experiment was, of course, that, I mean, if you go to very special initial shapes, this triangle, actually the whole, not only sort of, I mean, the potential energy sort of becomes periodic, but also sort of the form of this. And this is something very special, which, I mean, I think is a very special consequence of the initial condition, and in a way is not specifically tied. Well, scale invariance is a precondition for this to have, but I mean, you need more than this. It holds only for very special initial conditions. There are these two deep breathers, and there's some recent work by Huisai, which essentially sort of explains that observation. What I wanted to do now, sort of in the rest of the talk, is to say, I mean, is scale invariance also, does that also show up in more subtle properties of cold gases interacting systems, in the sense of, in a way, do transport coefficients show something special? And for this, I want to, in a way, start at a rather elementary level and say, I mean, what is if we go from an ideal fluid where there's sort of, in a way, no viscosity, nothing, to a real fluid where there's some viscosity or some heat transport? Now, the equation of motion, now, if you look at, for instance, the momentum balance for such a fluid in quite general terms, if it's isotropic and homogeneous, and it's a Newtonian fluid, there's local relations, was written down by Navier, a French engineer, about 200 years ago, and it was then further developed by Stokes in the years later, and it's called the Navier-Stokes equation. And in addition, sort of to the usual Newton's law, momentum balance, you get two terms where sort of, in a way, the momentum is dissipated. This is linear in velocity here, while this is the derivative of the velocity, which involve the shear and eta and the bulk viscosity zeta. And at this level, these are just phenomenological coefficients, which, I mean, the only thing you know about them is that they must be positive, because, I mean, in a non-equilibrium situation, there must be some entropy generation which must be positive, no more. And actually, sort of the definition of the shear viscosity goes back to Newton. You look at the shear force per area in such a situation where there's a shear in the sort of velocity field. And the shear force, I mean, has some very sort of important implication, namely, if you have a system where you have a flow of some sphere, say, in a fluid, you hold the sphere and you let the fluid pass, then to hold the sphere, you need some force, because the fluid would otherwise drag it along. And that's sort of what was determined by Stokes in 51. And at low velocities, it's just proportional to the velocity, and the eta, the shear viscosity, appears here. Now, it's clear if we have a superfluid, something like that does not appear. And we think, okay, in a superfluid, of course, there's no eta. And I will sort of, in a way, discuss that a bit, and in particular discuss, in a way, what do we know about, in a way, such forces, drag forces in normal and in superfluids. And I want to look at it at a local scale. Now, if you look at such a problem, and you look sort of in the frame of this, where you fix sort of the sphere. This is a stationary problem, and you can say, okay, the fact that you have this obstacle here produces some backflow. The fluid must go around this. And at low velocities, what you can always do is you can sort of expand this backflow pattern in powers of the velocity. The first term is the linear in the velocity. And since this backflow pattern must be stationary, so the divergence of this must be zero, the most general form it can have is this. So if you dot it with q to take the divergence, it must be zero. And so the only thing, in a way, you need to know for such a backflow problem is, for a stationary backflow problem, what is this function h of q? Now it turns out that if you look at this backflow in a way far from such an impurity, there's a kind of Laurent expansion for this h of q, and it contains the leading terms. There could be an h minus 2, which is actually there in Stokes' flow. There could be an h minus 1, and there's an h0. The h0, a constant here, which is actually a dimensionless constant in my units, is dipolar backflow. So if you take just Landau-Lifshitz and look at what the backflow is around the sphere of what Mr. Stokes has solved 170 years ago, you get h minus 2 is proportional to the radius and the density of the fluid. And there is no h minus 1, but there is a dipolar backflow. This is dimensionless, and the strength of the dipolar backflow is negative, and it just tells you how many particles have you excluded by your sphere. And if you then look at carefully which part of this flow gives rise to the force, then it turns out this dipolar backflow doesn't give any force. It's only this Stokes flow. The force from Stokes is given by this coefficient h minus 2. Now, in a superfluid, of course, we cannot have such a term. There is not such a term. There's also not such an h minus 1 term. But you can work out that there is a dipolar backflow around such an obstacle. And interestingly, and this is something that I think nobody has sort of in a way really realized, is that the strength of this is essentially minus twice that of the classical system. So if you would go from sort of in a way a fluid with a viscosity to a superfluid, the backflow around such an obstacle moving in a superfluid changes its sign. Interestingly, this whole piece, this h minus 1, has also an interesting history. Namely, this was predicted on qualitative grounds by Rolf Landauer in '57, and it was then calculated by myself 40 years later. Landauer was quite happy, but it has, in a way, never been seen. There's a so-called Landauer backflow, which is actually the one which is responsible for residual resistance in metals. People have tried, but it has never been seen. And it also, in a way, is missed in the textbook by Pines and Nozière. Pines and Nozière discuss backflow in Fermi liquids, but they don't have this term. Well, okay, because they calculate sort of in a way to linear in the order in the perturbation. But here you need to, this term only arises in second order. Okay, so let's come back to the issue about, in a way, viscosity in superfluids. And then, of course, you would say, well, I mean, of course, a superfluid doesn't have a viscosity. That was sort of the original definition of a superfluid. No viscosity, flows without friction. It's not the full truth. Because, I mean, at any finite temperature, there is some thermal component, and the thermal component gives rise to viscosity, which at low enough temperatures rises. The original prediction, 1 over t to the 5th power by Landau and Kalatnikov, actually sort of has been revised in recent years by Yvon Castin. Yvon Castin has spent quite some time looking at this problem quite carefully, and it depends a lot on the details of the excitation spectrum and on the interaction between quasi-particles. Anyway, the prediction is it grows up, and actually sort of this was seen a long time ago in sort of viscosity in helium-4. It shows a minimum, and then eventually in the superfluid regime goes up. So if you sort of torsional oscillator and look at sort of the damping of this, you can infer the viscosity, and you get sort of this non-monotonic behavior. So can we say something about this minimum here? Well, a simple argument would be just look at kinetic theory of gases. This is a bit strange, of course, for helium-4, but let's do it. In the kinetic theory of gases, viscosity is something like mass density times some average velocity times a mean free path, and there's a factor 3. Now you see, mean free path goes like 1 over density. Here there's density, so the density drops out. And you replace this average velocity by the thermal velocity with the momentum here, and the mean free path contains a scattering cross-section. So what you see here is density drops out. That actually was something, this was a prediction Maxwell made in 1868, that viscosity in gases is independent of density. People didn't believe him, said this is ridiculous, viscosity must increase with density. No, Maxwell said it doesn't. And he was right, and that was sort of in a way an argument for, I mean, these kinetic equations were not unreasonable. Now the question is, I mean, can one, I mean, from such an argument say something about perhaps what is the minimum viscosity that we can have? Well, you can say the mean free path could not be smaller than sort of the average interparticle spacing. And in a quantum system, the velocity, average velocity, could not be sort of less than h bar over m n times sort of the, again, effective sort of, if you wish, wave vector set by the density. And if you do this, and from the simple kinetic theory argument, you see again that the density drops out. Okay, now the density in that situation, there is with L and V, it gives a rise to a lower bound on the shear viscosity, which involves h bar times the density times a numerical factor. Such arguments were given some time ago by Szuriak, but of course they were sort of hand-waving, and we will come back to this, that, I mean, such arguments actually have more than just sort of hand-waving nature. Now, can viscosity be measured in cold gases? Well, this whole field of viscosities in cold gases was, I think, started by John Thomas et al., who has, in a way, in the last 10 years, made a number of experiments extracting viscosity from just looking at expansions of clouds. Here, for a scale invariant system, unitary fermions above in their normal state, expanding from an anisotropic configuration, an anisotropic trap. And this, upon expansion, you get an inversion of the aspect ratio. It expands quickly sort of in the direction where so you have a lot of interaction energy, and it expands slowly along sort of the weakly confined direction. And you can sort of follow the aspect ratio as a function of time in such an expansion, in a way as a function of the energy content of this gas, measured here in units of energy per particle, measured in units of the Fermi energy. And what you see is you can take, with the Feshbach resonance, go to the ballistic limit. Then in the ballistic limit, the aspect ratio just continuously goes to 1. There's no such an inversion of the expansion ratio. But in the regime of the strongly interacting gas at infinite scattering length, there is an inversion of the aspect ratio, and it can be described in a hydrodynamic manner, and you can extract viscosity coefficients. This was done by John Thomas in the last years. The problem with this is that, I mean, basically you are doing trapped averaged measurements, and you're also, in a way, of course, assuming hydrodynamics for the cloud, where you know at the edge of the cloud it's not, because it's too dense. And so to extract things from that is a very difficult business. But of course, what you can check is that this is one consequence of scale invariance in the system. If you look at the R squared, the total R squared, that actually has ballistic behavior, even though sort of you get this elliptic type flow, as he calls it, in the expansion. So these things were kind of, in a way, started quite some time ago, but in a way they were never really or very conclusive because of this problem: how do you connect hydrodynamic motion in the center of the cloud with sort of ballistic motion outside? Now, this whole, in a way, problem has two aspects which I think are quite amusing and interesting. One of them was again started by Felix and Yvon in 2006 and independently by Son, namely that one can show by general arguments that a scale invariant fluid, many-body fluid, cannot have a bulk viscosity. So the fact that in these experiments, this red curve, there's no contribution here to the bulk viscosity is, of course, consistent with this relation, but of course, it's just a consistency check. But the other story is, and this is something quite amazing, is that Kovtun, Son, and Starinets in 2005 on some rather sort of in a way strange, in a rather strange way, concluded or conjectured that if you take the ratio of entropy density of shear viscosity divided by entropy density, then this ratio is bounded below by universal constants of nature. And they were bold enough to check this relation, which is a quantum relation, but apparently has no velocity of light in it, so you can check it also for non-relativistic systems, for such mundane fluids like water. And what you find indeed that this ratio H over S in these units sort of grows at high temperature and it grows also at lower temperatures. Around here is the critical point, but then it has a minimum. But even for water, this minimum is about a factor of 30 above this bound. So it's above this bound, but you can say, well, come on, I mean, why is this quantum bound relevant for water at the critical temperature? Okay, I could go into some of these arguments why this happens to be true. Essentially, it's dimensional physics. And it has been sort of a very, I mean, startling prediction. And the funny thing is, all known fluids in nature obey it. There is no system which disobeys it. You can construct counterexamples mathematically. So in a way, it's not a strict thing, but in a way, all known fluids in nature obey it. And so the question, I mean, that could be raised is, I mean, maybe are there systems, and in particular with cold gases, and this is already something that was mentioned in this paper in 2005 by Son et al. Maybe cold gases could be tested and could realize what they called at that time sort of the most perfect fluid. How can you calculate a shear viscosity? Now that becomes, to really sort of do an honest calculation, becomes quite messy, because in principle there is of course a Kubo formula for all such transport coefficients, which allows you to determine even the frequency dependent shear viscosity from a correlation function, some retarded commutator of the stress tensor. But of course the stress tensor in an interacting system is a complicated beast. It simplifies a bit for zero range interaction, but it becomes very complicated. Nevertheless, in a way, we were able, within a certain approximation, to calculate this, and in particular, calculate this eta over S. And it is sort of in a not very exciting, in a normal state of a scale invariant system. At high temperatures, this grows like T to the 3/2. And then, in a way, at low temperatures, a bit above Tc, it actually shows a very slight minimum, but I mean, it's essentially settles to a plateau. At below Tc, we cannot calculate it because it becomes too complicated, but it's relatively plausible that sort of eventually sort of it increases here. So, and you see here the minimum value is around 0.5. This is still about a factor of 5 or 6 above this bound, so it's consistent with the bound, but it's actually sort of the system with the smallest value of eta of S ever known for a non-relativistic system. And Thomas Schäfer in the recent years, together with his collaborators, has carefully looked at the old data of John Thomas and sort of reanalyzed this in a way properly taking into account this transition from hydrodynamic flow to the boundary, to ballistic flow in the boundary. And so with these calculations, what he gets is sort of in a way a confidence band where sort of the eta of S ratio as a function of T over dF holds. And in a way, it's extremely close to what we had predicted. So this is, and also for this eta over N, the results we got from this old paper seem to be sort of very good in the normal regime. And so basically one conclusion of this is that one can say this unitary Fermi gas, so a scale-invariant many-body system, is one which realizes a minimum in viscosity to entropy density ratio, which is about 5 or 6 times above this bound given by Son et al. Actually, sort of these systems, in a way, this is in a way systems which have sort of the shortest time of mean-free path you can have, essentially set by the interparticle spacing. And the whole story was, I mean, became also in a way more, I mean, more careful measurements of such transport properties have been possible recently by just looking at damping of sound waves. This is something that was done at MIT in the group of Martin, where he took a Fermi gas in a box, did shake the wall, then saw just density waves, and determined sort of course, the velocity. That was in a way not so exciting, but also the damping of these sound modes. And hydrodynamic damping of sound modes gives diffusive damping with a diffusion constant d sub s, sound diffusion constant, which contains the shear viscosity and also the thermal viscosity. So if you measure this and if you know the shear part, you can also determine sort of in a way thermal conductivity in such a system. He verified that the damping is actually sort of going like the frequency of the wave vector squared. And since we know essentially the shear viscosity and we know this thermodynamic factor, which is the Landau-Platschek ratio, we can infer the thermal diffusion constant. And this is something that we calculated not relatively recently, in a way based on, well, Fourier, again, 200 years ago, wrote down sort of this law for heat current being linear proportional to the gradient of the temperature. And there's a Kubo formula for heat currents, which is a bit subtle because, of course, there's no perturbation in the Hamiltonian, which gives rise to that. Where actually the heat current is energy current minus sort of enthalpy per particle times particle current. And from these calculations, we are able to determine heat conductivity and also the thermal diffusion constant as a function of temperature in the scale invariant system. And let's focus here on this 2 diffusion constant. The blue is the sound diffusion constant measured by Martin Zwerger. Sort of it's is sort of in over a reasonable, not too large, unfortunately, interval of temperatures in good agreement with what we found. And you see the units here are h bar over m. Diffusion constant have units h bar over m. That's the natural scale for diffusion constants. And for any scale invariant systems, you get something like this. But then, I mean, what eventually sort of, if you look at the contribution form, the thermal diffusion constant, that should eventually sort of at low temperatures go up because, of course, in a superfluid, there's no thermal diffusion. Then there is, in a way, entropy is propagated by waves and not diffusively. And that's, in a way, unfortunately, not seen. If you just extract sort of the thermal conductivity here, you see, I mean, that would be, the red would be sort of the prediction that eventually sort of it should go up here. But, I mean, the experiments don't show it. But what is interesting is that thermal diffusion constant in this regime of sort of a strongly interacting scale invariant system is about 10 or 11 times larger than shear diffusion. So so in a way, thermal conductivity is much better than shear diffusion, which in a way often, I think, allows you to justify the often made assumption that somehow, I mean, even in a non-equilibrium situation, I mean, the cloud is sort of reasonably well equilibrated in temperature. The thermal diffusion constant is much quicker than sort of other transport properties. What about going away from scale invariance? Well, of course, if you go away from scale invariance, then there will be some finite shear viscosity. This was discussed first by Schäfer and then by Yosuke Nishida in recent years. And one of the sort of nice ways to see that would be you measure, in a way, the energy deposited by sort of a periodic change in the scattering length. If you can periodically change the scattering length, even around infinite scattering length, you get an absorbed energy which is proportional to the real part of this bulk viscosity. And the bulk viscosity is finite, even sort of in a way the combination that comes in is even near the superfluid, near infinite scattering length, so it has been calculated by Tillmann Entz some time ago. And in particular also, for instance, if you could do such an experiment in a 2D Bose gas, there's a simple prediction, at least for a dilute and sort of moderately degenerate limit, that essentially the bulk viscosity has again sort of this natural units h bar times density. Here you see the phase space density, and then all the interactions come into this logarithmic factor. Now you see if your 2D scattering length is tiny, as it is, sort of this binding energy would be very large, and so this logarithm becomes large. But if you have, so in the situation with rubidium-87, I mean, this logarithm in a way kills you, so it becomes super small. But if you could realize a situation where sort of you have a 2D gas with a G tilde of order 1, then I think sort of such a contribution to the bulk viscosity would show up and would be sort of interesting to investigate, because I mean, in a way, the dependence on density and temperature is essentially set by dimensional arguments. So this concludes the talk here. So I have argued that in ultracold gases, we have a number of concrete realizations for scale invariant many-probability problems, both in any dimension, 1D, 2D, 3D, and you have additional symmetries which give rise to, I mean, a number of features that, I mean, you don't have in systems that are not scale invariant. In particular, I focused on these transport coefficients, which in a way have quantum limited values. So typically, if you express things in terms of some diffusion constant, you always get numbers times h bar over m. One interesting thing that in a way I think has not been measured so far and would be sort of nice to see eventually is some, in a way, going away from scale invariance and see some appearance of a bulk viscosity term which is not there in a scale invariant system. So this is in a way the last one of my talks, and I hope that, these talks have contributed in a way for at least some of you to a better understanding of some general features of cold gases. It's of course not easy sort of to address the level of all the people here in the audience. I've tried sort of to make contact, of course, also to experiments. For me, I think it was quite a nice experience to be here. I thank you for the invitation, and I will just end with saying au revoir, merci beaucoup pour votre attention. Okay.